Well, welcome everyone. For those of you that don't know who I am, I'm John Toole, the Executive Director and CEO of the Computer Museum History Center. I want to welcome everyone. We are really fortunate to have our lecture this evening, and I know it's going to be a fantastic one, to say the least. And I'll talk about Fran in just a moment. Many of her friends have came down from with her, and I'm really excited. And I've talked to a few of them, Fran. They're really a wonderful group of folks. The Computer Museum History Center, of course, is really dedicated to the preservation of the artifacts and stories of the information age. And I hope you all take a chance to look at our display out front of where we're going to be headed with our partnership with NASA, with both putting a new building up in 2004. We currently have a visible storage area, which I hope many of you have seen. In fact, let me offer you right now, those of you that came in town with Fran, I'd be more than happy to personally give you a tour tomorrow morning if anyone would like to do so. I'd be like to show you through our own visible storage area over at Moffett, if you just let me know immediately afterwards. It's an exciting time. As I mentioned before, I've only been here 6 months myself, but it's unbelievable the dedication, commitment, and drive, motivation, and importance it is for all of us right now. Having said that, we're co-sponsoring this event today by the Institute for Women in Technology, Anita Borg. The Institute was founded in '97 by Anita with its mission to increase the impact of women on all aspects of technology and to increase the positive impact of technology on the lives of all world's women. And we're really proud to be a co-host with them this evening. Let me now introduce our guest speaker, who's going to excite us all. Not only is Fran, of course, one of the most positive people I have ever met, and continues to be one of the most positive people for all the years that we've known each other, she's really a pioneer in the industry. And we're very, very honored to induct her tomorrow evening at our Fellows Awards dinner as a fellow of the Computer Museum History Center. But she's really been a pioneer in optimizing compilers in a lot of different specialties. Her specialty, of course, has been the development of advanced compilers for program optimization, and her achievements include seminal work in compilers, code optimizations, and parallelizations. And of course, she's helped create the first automatic debugging systems and a member of the Stretch team. The Harvest project really helped keep an advanced role in code-breaking languages. And I think we're going to hear a little bit about that. And of course, Whit is here too to really understand kind of what it was like back in those times. Really, Fran served as a technical consultant for it was right now, I guess, in the Blue Gene project, the way I understand it, and at the petaflop computer for protein folding. And in 1987, she was elected to the National Academy of Engineering. In 1989, she became the first woman to be named an IBM Fellow. And she became president of the IBM Academy of Technology in 1995. But her enthusiasm, spirit, and friendship, please welcome Fran Allen. Thank you, Fran.
Well, it's great to be here, and I want to thank the Computer Museum for inviting me, in part because it was an opportunity to go back and think about an old project that I hadn't thought about a lot recently. In fact, John and others had said, just pick a project, pick something you want to talk about. And I thought, well, I'll talk about compilers. Well, I'll talk about the Advanced Computing Systems project that Don Rosenberg and I were on. And I'll talk about this, and then I said, I'm going to talk about Harvest because not much is known about that. It was a project for the National Security Agency at a time when it was not known that the National Security Agency existed, and and so not a terrific amount has been written about it. So I decided that's why I picked that topic, and I'm delighted to see so many friends here. In particular, there are at least two people from that project. Ann Hardy was a colleague of mine on the project, and we'd actually worked together before. Ann, you want to? And Norm Hardy was on the stretch side of the project, was also on the project, having joined the project from, I guess, on sabbatical or as from Livermore, where they were getting a stretch machine. So, and I've worked with a number of other people that are in the room. It's really, and had a great deal of fun putting this together. Anyway, what I'm going to talk about is harvest for NSA. And let's see, I'm trying to avoid this light here. I guess I'll have to move this over a little bit. And then I'm going to talk about the language alpha for harvest and the compiler for alpha. I'm really not going to talk a lot about the compiler because I realized in order to talk about the compiler, I had to talk about the language. And in order to talk about the language and the compiler, I had to talk about the machine. And so we don't have enough time in an hour to talk about all of those things in great detail. But one thing, the talk is not about stretch, though stretch was a part of harvest. There's a lot of information about stretch that's available. Buchholz's wonderful book that he edited and was published in 1962, and called, what is it called, the project, something about, I've got a reference to it later anyway. Should be required reading, I think, by anybody that's going to be building a machine. I had great fun looking at it, reading it again. But I'm not going to, so there is a lot of information available about that particular project. And I'm going to talk a little bit as we go about the state of the art and its times, and I'm going to end up with a question as well as some perspectives. Actually, Ann and I were just talking about the question that I'm going to pose. Okay, what are some of the timelines that are associated with this project? In 1954, the Stretch project was initiated, and in that same year, about the same time, the National Security Agency came to IBM Research and asked them to do a study on a new system for their problem, code breaking. And then, so as a result of that study, a contract was signed at the end of April in 1958, and the project started in 1958 in May, and was actually delivered then to NSA in 1962, 4 years later. So keep the fact of what happened in that 4 years from the time that the Harvest project started and that machine was delivered. You're going to see some pretty surprising information, I think, about, if you haven't looked at Harvest before, about the size and complexity of that project. The project then, actually the year before that, Stretch went to Los Alamos, and in 1976, 14 years after it had been delivered to the National Security Agency, the Harvest machine was retired, and I'll tell you in a few minutes about why it was taken out. And Peter Capek, back here, can tell you what actually happened to the hardware. You can catch him later. Peter, you want to wave and raise your hand? He told that to me on the plane last night. I hadn't heard it. Okay, this is what the Harvest system looked like in terms of a diagram. It has this part of the line, this side of the line is the Stretch system, the 7030 system. And then Harvest, which is called the 7950 system, is on this side of the line, this dotted line in the middle. And it contained a central processing unit and a high-speed tractor tape system, as it was known. And it's mostly these two parts of the system that I'll talk a little bit about, describing what they are. The total system, and you had to actually run programs from to control the Harvest side, were actually run on the Stretch side over here. There was also a lot of I/O, and the memory. You might take a look at those. That they were on the slow memory, 2.1 microseconds at the time, had 16,384 words each. these were 64-bit words, 8-bit bytes, and it was, Stretch by itself was one of the greatest machines to program. It was my favorite machine of any machine I ever programmed, because one could address any bit in the machine and protect any word. So, and the word boundaries, references could cross word boundaries. So it was really a marvelous machine to program, and as a Harvest was programmed very, very differently, as we'll see. In fact, Harvest itself, and in doing some of the reading, I came up with the fact that it's more than twice the size of Stretch, and I think that's just the Harvest side, which referring to the processing unit and the tapes, and it had 500,000 transistors. I don't know how you ever built something like this at that time. And Stretch was much smaller. Probably in this case, this document was counting the total number of transistors in both machines. I don't know. It doesn't matter. Still a very large number. And the number of instructions was listed as about 250,000. That's because the Harvest processing unit was really a micro-coded machine, and you had to code it against the timing, and so there was that number of instructions were the total number of possibilities of different kinds of operating modes that one could have. But Stretch was a pretty ambitious machine itself in a more traditional mode of having 735 instructions. And when I talked to Jim Pomerine recently, he mentioned, Jim was the chief engineer from IBM for building Harvest, and had a long history with NSA, and in fact had worked at Princeton with John von Neumann on an earlier machine. So but he pointed out to me that it's the only system that has been built, I think he means, with balanced I/O and computational speeds. And I'll give you a little bit more information on that in a minute. The other part of the system, which some of the NSA people felt was even more interesting, beyond the processing unit, was where the tractor tape. And here's a picture of the tractor tape that I pulled off the NSA website. NSA has really come out. They have a website, they have a museum. They actually have a museum on the site outside the gates, as they call it, which is in the place where there used to be a motel that we used to stay when we were going down there. And I actually, and a lot of people have, because there were so many of these, have a tractor tape in my office without any tape. When it left the NSA, they took the tape off. There was no possibility of it, any information escaping. The tractor itself was a system where you had the cartridges of that, which were about like this big, and there were 160 such cartridges per handler, and 3 of these big handler units were attached to the machine. In fact, the tape, a tape on a cartridge, could store 90 million characters, and the transfer rate was over 1 million read-write transfer rate. So you could have 3 cartridges in action at the same time. So what ended up is the maximum read-write transfer rate was over 3.3 megabytes per second, and in fact it matched the streaming unit. This was the matching that Jim Pomerine told me about, which I somehow had forgotten or never knew, like lots of things about Stretch in the Harvest. But it really was balanced with the streaming rate, which would go through the processing unit. Also, because the idea was nobody would ever touch the cartridges themselves, and had automatic error checking and error correction built onto the tape. The tape was about 1.7 inches instead of about the traditional half-inch at that time. So it was indeed a rather amazing system. Now I'm going to go back to the streaming unit. This is a very simplified version of the unit, and I'll get to a slightly more complicated one in a minute. But the point I want to make with this one is that it goes through the memory, both the slower memory and the fast memory that we saw in the earlier diagram, and information could come from memory in streams at the rates I was talking about, and into then a unit, one of two units, both units at the same time in parallel, and a lot would then be where what was happening in the units is actually the selection process of what data to bring up. Indexing would happen there, and happen in such a way that the streams could be kept moving in steadily. And then went through the transformation process, and I'll show you some of the transformations. I'm not going to show you all of the thousands of instructions, and then producing a result. Oh, what? Oh, some of my diagrams. I should have put this on here. Some of the diagrams most of them came out of the Buchholz book, and this was in that Buchholz book, but I actually extracted it from an earlier paper by Paul Hurwitz, and Paul Hurwitz had written a paper, and then he and Jim Pomerine published that paper in the 1960 Western Joint Computer Conference, and it also ended up in a small variant as a chapter in the Buchholz book. So I don't know where I actually copied this from, but it was the same diagram that floated around through the three papers, three areas. I should, in fact, since I've collected up a lot of information here, should probably at some point in the future put this together into an essay of some sort, or a paper with pointers. This is this is definitely from the Hurwitz book. This shows in a little bit more elaborate, more detail information about the units. So this is of course a bus to memory, and this is an indexing unit which then determines what to do with the data that is arriving from memory, and there's a huge 128 by 8 matrix here, which kind of can pick out pieces of data from the streams that are coming in. So this is an elaborate unit. The indexing unit itself had, according to the document, it had an unlimited number of levels of indexing. But I'm sure there was some level. But it was a large stack of indexing parameters that were set up ahead of time, levels of indexing, which then could pick off various pieces of the streams, and actually you could put whole do loops, for example, if that was the way it was written, into a single stream indexing unit, picking off the operand. And there's, as you'll see in the alpha language itself, there was within statement indexing, there was actually these statements were matched the streaming units pretty closely in the language itself. Over here is a mask register so that you can actually pick off, look for information in the unit. For example, you can look for various special characters, and then and make decisions about whether where to forward them into other parts of the transformation. Same thing was true of the other input unit, and over here one sees some capabilities associated with assembling tables and extracting information out of tables, again with their index units and some logic units also, and then putting things back into storage. What's missing from this diagram is another huge adjustments that can be made on the fly to the indexing or to the activities, so that one doesn't have to go back to find something, then realize one wants to make an adjustment in the indexing or in tables or change whole sections of address, and one doesn't have to go back to I speak about this in the present tense. I found, but one didn't have to go back to stretch which would be expensive and drain the machine. One could just continue making on-the-fly adjustments to the tables that were entered in. Here are some of the harvest processing modes. The one we used all the time was a stream byte by byte. By the way, I didn't mention this was for code breaking. Did I mention that? NSA, I sort of, but it was, and we, though I had a Q clearance, and I never saw any of the code breaking code. And it was a long time before I even was certain what it was for. I was never really told what it was for until I read it in the New York Times. But clearly this first instruction, and one shouldn't think of these instructions. These are modes of setting up the data streams through the machine. Was the stream byte by byte here, so that one could have hold one stream and then stream all of the data on another stream against pieces of it. You could chunk off and want to look at sections of the data, or one could do statistical analysis of the streams and find matches. One could stream them and together, and then do and many different kinds of variants. There was another interesting one, the merge, which allowed two streams to be merged under various conditions. And a variant of that was the sort, which is down near the bottom here, which was one could sort data as a single, and it was an operation where one had the size of the data, the size of the area that one was sorting was some power of 2. One would then had to be a power of 2, and you'd have a buffer area, which was also another of the same size, and it would be kind of a bucket sort back and forth. So you can see it was kind of also combined with the merge. And again, the adjustments would allow one to actually do a sort on data that was bigger than memory, the storage. And then the others select stream indirect load and store, stream multiple lookup, sequential table lookup, and one where you could clear the 2 microsecond memory in one instruction in about 2 microseconds, or 2.2 microseconds. It was really, and that was the 16 K words. So this was a machine which was designed, I think, as very much for the problem, and very much integrated, with the stretch capabilities, with the memory capabilities, with the I/O capabilities, and in fact, it was designed in some sense in a holistic way, because the alpha language, which I'll talk about, and the something called the harvest operating system, which controlled the operation of the entire machine, was all designed together. Now I want to switch to the alpha language. I was quite involved with this language, and worked with was the liaison between IBM and the people at NSA who were working on the language. Great people. I really enjoyed working with the NSA people. I remember particularly there was a guy named John Guy that I worked with very closely, and just these are the unnamed heroes of much of the work on Harvest, and on code breaking and a lot of other things. A lot of respect for them. They did great things. Anyway, in 1968, remember Harvest was delivered and was functioning in 62, and it functioned for 14 years. So it was in 1968, there was a paper written about Harvest, a very 4 or 5 pages, which is was secret at the time, of course, but is now been declassified. And the librarian at the museum there sent me a copy. So, and this is what the intent of the alpha language was for. It's available, is also available, this was in this little document, is a far more advanced language called alpha that approximates the language of cryptology, one that permits the programmer or cryptologist to use English words to refer to a sequence of logical operations. With this language, a complex problem can be prepared for the computer in a matter of days rather than weeks or months, and that was actually borne out subsequently. Okay, I want to spend a little bit of time on this language. Going into it. The language first. I want to talk a little bit about the data and not as much about the instructions. The Harvest operating system, which would probably be called the Harvest operating environment, which had included all of this, had several built-in data types, the usual int, float, binaries, basic, and then 2 more called Harvest CS1, character set 1, which was the 48 characters that one could print and could be on a key punch that you could type in on a key punch. And HCS2, the 256 characters represented by digits, 1 to 3 digits. And then we had 2 unique characters, pad for blank or null, and which was always first in a sequence. These were always, the sequence for the data types was an important aspect of the data, because then one would know how to sort it and so forth. And something called scab for bad or illegal. Now, of course, the application involved listening in listening stations all over the world, and a lot of the data that came in was very, very bad, but one needed to be able to process it, and so that this was intended for illegal data, or just to that because of the way the data had been gathered, or just that it was illegal for other reasons. So it would be the last in the sequence. That I might say, I won't go into the story, but that their placement in the sequence created us great difficulties, having to do with what's a 0. And the alphabets then, which were defined on the data, were ordered sets of characters defined on one of those, the Harvest character set. And there were some standards built into the system, the English alphabet, the decimal alphabet, the alphanumeric, and the base alphabets. And then the new alphabets could be introduced, defined by the user. The vowels, here's an example of vowels, which you could define that as an is based on the HCS one system. Alph is actually just the operator that in the language, and it's A, E, I, O, U, and together with that would be the character for blank and the character for scab, for Ben. And the Cyrillic alphabet, however that gets, one decided to define that. Then one could operate with, you could write a program which could operate on different kinds of data streams and not have to change the program. So one analysis could be done on the Cyrillic alphabet, on a Cyrillic stream or whatever stream, as long as the codings had worked out. What?
Surprised Cyrillic wasn't built in.
I am too, given the times. But there was a very standard mapping for it that everybody was pretty familiar with. And the data structures then there were strings, multi-level strings. There was something called chords. I never liked this terminology, chords. Starting with strings, we got chords and ropes. Chords were a sequence of strings, and that again could be multi-leveled and so forth. And ropes is an array of records, really. That's what chords really are. And then we had graphs, which really weren't identified, named specifically, but they were used. They would be implicit in an operation which was on various kinds of k-graphs, looking to locate, count, or extract occurrences. Yeah?
Were these designed by NSA, or the alpha language? Where did it come from?
Well, the alpha language was designed by NSA, and I was part of that team. But the primary design of it came from NSA, right? But we were doing the compiler, we being Anne and myself and a few others. And so what the role that we were playing, or I was playing, was on its compilability. And yes, and I disagreed with John Guy about that. We had a good discussion, but that was their. But it was not something that they had before. I mean, much of what they had done in the Harvest project was brand new for them, also.
Chords and ropes in the 70s. There was a paper in Software Practice and Experience.
Oh, that's interesting. I'd be interested to find out.
Yeah.
Well, there is a paper. There was a document after the alpha language document. The first, it was classified, but available within IBM. I mean, it wasn't classified as secret or anything like that. And in 1962, first I have both versions of it: the original version, working version, and then the final version, which came out late in the year. But there was a beta document that came out in 1969, which somebody gave me. And again, it was a follow-on to the alpha language, and I think it still used that. And I think it was more available. So that's probably where that came from.
Did your compiler go through beta tests?
One of the reasons I think we were so successful in getting things done then is that we didn't have any processes. We also had some disasters, but here's another. The alpha indexing one could have, in addition to the usual arithmetic progression, where index sets were permitted, and one could have both parallel indexing and rectangular. and the indexing could be in the usual do loops, but also within statements. So here's an example of a statement here where there's a parallel index. I is 8, goes from 8 to 6 by -2, and k is going to go over the index set 372, and it's going to run in parallel. So this would reference the operands 8 items 8, 3, and then it would go have the index at 6, 7, and then stop because this index would, the first index that's out of that finishes the operation. So, and these, so this is was an important part of the language because it was with that very long specification of the indices attached to a statement that one could build up the index sets for the streaming unit. And then another thing Alpha had was data implication. Was it was really determined to determine the descriptors of data. One didn't have to define all of the data. Identifiers didn't need explicit descriptors, but a statement result descriptor could be determined from the operation and its inputs. Look at the statement, and it was done by the compiler. That was a part of the compiler's job, was to do that. And in order for that to work, the statement ordering had to be such that all of the input operands had data definitions by the time one was analyzing the statement, and then one could determine the data descriptor for the result. And so, and these descriptors then, which were determined at compile time, would determine the size of the memory area allocated. There was a parameter system which could then actually determine that size, but not dynamically during runtime. In fact, there was, and then there was reshape and redefine, which was like a overlay on top of existing data in order to give it a different name and a different type, different descriptor. There was in the system I mentioned there was something called pre-run, which one could actually, having put together the entire application in which might take days to run, then there were parameters that would be passed forward, to restart different sections of the application, and there would be one of the things that the system did was actually make a check to make sure that you had to put together a valid application in which the parameters were correct, appeared to be correct before the real application was run. We give a little. This is a mini example, and it's not very the only example of the language use I have, because it gets down into some messy stuff with programming. But here's an example of something that's a couple of strings. One is a two-dimensional set over here. Then there's something else which is called sublines, which again is also a couple of strings, but there are an array of those, records of a couple strings here. Well, actually, a two-dimensional string is part of it. A table, this is something else called a table, and here's the use of parameters, which is again a record. And then in here, one sees something called subtract. Sub is a subtract. The second part of this first object, mess. So this part here, and subtract sublines from that, which would be this object. So this object here was subtracted from that object. Okay? And that then would give something which is called difference, which would be a 10 by 4 decimal as a result. And that was data implication. One could deduce what that was. Also, you can see that the indexing here is deeper because, of course, one is having to go through strings of these things. But one can and set up that indexing can be set up for the machine automatically. And for big arrays, one could address large units. And then in this one is an example of this is a fragment of a program that the person I was working with at NSA wrote, John Guy, and it it shows taking the table. It says that locate the 4 graphs in table such that this is satisfied. This table 1. This is the K, which is going to run over the whole array of records, chords, and then 1 will pick out the fact that it's this first subrecord, and 1 here then picks out what it is. Pick out table on. Oh, what picks out starting with the first decimal here in that string, equal to the other one, and then in here one can see this is is not parallel. This is nested indexing, and it says max L1. That is a statement that says drop out the first time you find it, or accept only one value. You can say max L anything, and it'll accept the first whatever. It's a way of dropping, finishing quickly, and then there's a data implication and a reshape in order to continue with this program. Anyway, that's the kind of things that people would write, and in which the compiler had to compile. There were other, of course, alpha statement classes, lots of them, and they mapped very, very closely to what was in the harvest machine. So there were locate occurrences of k-graphs, extract occurrences of k-graphs, do lots of counting things, table lookup, merging and sorting. So pretty close mapping from a statement to the kinds of things it would be to an operation on the machine. So let me turn to the compiler, and I want to take a quote from Fred Brooks. This is because he always has something really very interesting to say. But again, it's in the Buchholz book, and this was about stretch. But a similar statement was made by some of the NSA people about the role of the compiler in these systems. And I want to read this. The objective of economic efficiency was understood to imply minimizing the cost of answers, not just the cost of hardware. And this was right at the beginning of the Buchholz book, in which Fred Brooks was writing down the objectives and the goals of the system. What had they talked about in doing the design? A consequent objective was to make programming easier, not necessarily for trivial problems, but for problems worthy of the computer. Problems whose coding in machine language would usually be generated automatically by a compiler, his italics, from statements in the user's language. So the compiler was an integral part of the system here on stretch and on harvest. And I think that one of the things we don't do that this is not something that often comes up in the design of machines today. It did on the RISC machine, with the 801 machine. Certainly the compiler was designed before the machine was, as a part of the machine. On a machine, on a project I was on after the Harvest project, the Advanced Computing Systems project, the one Don Rosenberg was on, and others here, I'm sure, and in which we worked on the compiler for a year or two before settling very much on the machine. I wish that were true today on my current project. Trying to make that and do something with that about that. So here is what the compiler looked like. Now, compiling for Harvest was a pretty big challenge, as you might guess, with the alpha language. But we made it even bigger by deciding we were going to it would be one compiler for Stretch and Harvest. Down at the bottom, there's object code, could go to Stretch or it can go to a Stretch Harvest machine, and to take multiple source languages. Fortran, Autocoder 2, which was a little bit like COBOL, I guess. I don't remember much about that. Maybe Ann does. And Norm, and the alpha language. And the structure of the compiler was that it went through, parser kind of thing, and then to an intermediate language form. There was an optimizer, and which produced another intermediate language form, lower level, register allocation, which then went lower level and into the assembly program. Now, one of the reasons, there's several things I wanted to say here. One thing is that this intermediate language level was a programmable level, and actually, the person who was using the system could get an external form of the program at that level. And on the Harvest system, this level down here, I think it was this level. No, I guess it was this level, was also accessible from outside, so that the programmer could go actually take the output there, tinker with the code, and continue. So this was a humongous challenge, huge challenge, and the state of the art at this time. Remember, this is in 1959 that we were designing this compiler. Ann's nodding. we were, and in 1959, Fortran had come out in April of 1957, so 2 years earlier. Though by the time we had finished the project in 1962, there was already Fortran 4, but the state of the art in there was, and that we drew on very strongly, was the Fortran compiler design, and though we went well beyond it. And the Fortran compiler design actually had multi levels too, and multi ILs, and had actually started many of the forms of the compiler that we see today. If you look at compilers and go back and look at what was in Fortran, the original Fortran compiler, there's amazing similarities, and certainly one sees a bit of it in this. Parsing was just starting to emerge, lots and lots of activity in it, and formal language definitions, lots of activity in this in this period, and in optimization, lots of activity to register allocation that everybody struggled with, and they're still struggling with sometimes. But on Harvest itself, we as many as we wanted. They weren't coded as registers. It was a stack of statements about what the index and what its relationship was to other indexes, just by the way where it appeared on the stack and what it was referencing, and then how it was to progress. So it was unlimited. See, it seems to me I wanted to say something else about this particular one. A stretch. Ran on stretch. And, oh, yeah. Just back on some of the technologies. Lisp were just starting to get popular. And I had one of the guys that worked for me, or worked for Ann, I've forgotten. They came in one weekend, and we were not using Lisp at all. We were using, just tables, and you'd have the symbol table, and then one would hang some stuff off that, blocks of stuff. It was kind of a mess because you had to manage these fixed blocks. These guys came in and transformed our whole system over the weekend into a Lisp-based system. And I was horrified on Monday morning about what had happened. But it worked, so this is the... It was written in assembly language.
Can we infer from this diagram that alpha could be compiled to stretch-only code and run without the harvest?
No, you can't. No.
Okay.
No. The reality was not that. Right. No, we didn't attempt that. Right. And the other thing is that hashing. The idea of hashing was really quite new, and again, actually in this case, somebody in the group talked us in, and I think Anna and I, into using hashing. Here we were trying to match a schedule, trying to get things delivered, and these people were picking up this wonderful new technology that had appeared and stuffing it into our compiler. But hashing went in, it worked beautifully, and I think really helped the compiler a lot. While I'm on this picture, though, should mention something about the stretch machine. The stretch machine, and again, was originally the original goal was that it would be 100 times faster than the 704, which was the machine of the time at that time, and in fact, one of the machine itself wasn't, and the stretch has every interesting story. The stretch itself, which was originally built for Los Alamos, and then after it proved, the machine itself proved not to be that fast. Well, it's kind of a long story, which is written up in Buchholz and elsewhere, about the machine itself. Then was decommissioned. Where the decision was made, lower the price, and only built nine of them because it didn't meet the goals that had originally been set. But the reason I'm telling this story here is that one of the things that I think the compiler contributed, though we weren't blamed for it, fortunately, is that on the Fortran side, we were delivering a weather prediction code, written in Fortran, and because of the slowness of the compiler, the slowness in fact, we weren't focusing as much as we should have on the optimization and on some of the components in here. Because we're going to have such a fast machine, we don't have to worry about speed, right? I've heard that story. Well, anyway, our Fortran version of the weather prediction code took 18 hours of execution to do a 24-hour forecast. So it was didn't contribute to the success on this side. That's fine.
Where do cards appear in this diagram? Punch cards. Just at the top?
Actually, no, you could, at this level here, at this IL, you could get a printout of it, and you could then punch that and actually work with it. That was called, it was all called autocoder 1 in one variant of the project. And then down further, and I've forgotten whether it was here or here, one could also get punch cards out and then work with it. At the end of this project, by the time the project was finished, 1962, Fortran 4 was actually being used. And so Fortran went from Fortran 0 without subroutines essentially in 1957 to a much more sophisticated language over the course of this project.
Cartridge tapes for things like this. Cartridge tapes are only for other kind of data.
Yeah, we did that. There was a big bank of regular tapes attached to Stretch, and that was all handled on the Stretch side. And the operating system was on the Stretch, or the Harvest operating system was on the tractor tapes, and partly because it was had to be brought in, but it was because the tapes were so heavily used. It was interesting to see the tapes wore out, and you could actually, but their error correcting and code, the tape would just be spinning, looking for the next good piece, and it could find it, but one would just observe that that tape had to be replaced. Let me move along here. So this is what were. There were a lot of, this was a great system to be part of. This was my second system, but it was not the other early one. What? But I wanted to mention just a few things that kind of happened along the way that I personally remembered, and I'm sure that Ann and Norm and others can remember some others, is that the project started with the software part, the compiler part that I was involved with, but all of the software part. Is built up around 1959. I had joined IBM in 1957 in the research division, and had worked on a couple of other things, but in 1959, a year before these projects were supposed to be delivered, the target date for both projects was 1960. Okay, these are Harvest starting in 57 and 58, and was supposed to be delivered in 2 years with all of this hardware and software. And around 1959, people got pretty concerned, and a whole bunch of us from research went to Poughkeepsie, were loaned to Poughkeepsie Development to work on it. And in fact, the Harvest, the compiler really got started when we arrived. Ann was part of that group, and we were located. They rented a tie factory in downtown Poughkeepsie, and a whole tie factory, and we worked in there. And then in 1962, 2 years late, I guess, the Harvest system was delivered to NSA. And I and a few others that had been working on the Harvest side mostly went down and spent a year there. During this period, NSA, there were two defectors from NSA. I've forgotten, two well-known spies. Who were they? Mitchell and Martin, okay. went to Russia, left NSA and went to Russia, and the New York Times, I guess, blew NSA's cover or whatever. It was known before then as the Bureau of Ships. That was the budget line under which all of this was done. And it was never an association between the Bureau of Ships and NSA. And I don't think NSA was mentioned at all. Suddenly, the New York Times had this huge article about NSA and about code breaking and about the defection. And that's where, it really is true, that's where I found out what I was working on. It was really, I don't know how I could have been quite so dumb, but I was. And so the other thing that happened after the machine was delivered in I believe it was March of 1962. And then in October of 1962, it was the Bay of Pigs as part of the Cuban Missile Crisis. And that was, I don't know what role Harvest played in that. I think there is some literature on it, which I haven't looked at. But it did have, it was at NSA, and being there at that time one could just sense. Of course, we had no one there knew what it was about, but everybody was on edge. All leaves were canceled. Everything just tightened down, and I remember the Harvest, which had a huge printer. It was constantly draped with black cloth. So if you happened to walk by it, you couldn't see anything about what was coming out of that. I told you about the story about the weather prediction on Stretch, and my final role on the project, I think I was probably the last person, at least on the software side, was to write the acceptance test for the machine, which wasn't a program to automatically abstract articles. I think these were Time magazine articles, as I remember, and so I wrote an alpha program to do that, and I was very pleased with how well it did. Of course, everything had to be turned over in the end, and I wrote a little final report associated with the project, which was had to turn over, could write but not read, one of those situations. Yes.
It was a unique machine?
Right. So I'm running way over. I hope you don't mind. I do know that the reception doesn't start until 7:30, I guess.
When you're done.
Huh?
It starts when you're done.
Oh, okay. So just want to finish up a couple things about the Harvest. This was this November 1968 report, which I referred to, which has been declassified, had this piece of information in it. It said recently Harvest scanned 7 million something messages of approximately 500 characters each, examining every possible offset to see if they contained any of 7,000 different words or phrases. This required 3 hours and 50 minutes to complete, an average of over 30 messages a minute. It was really a powerhouse for the agency, and I think all indications are this was a wonderful, an extraordinarily good machine for them, and it actually ran very well in terms of reliability for the 14 years. The reason, by the way, I didn't tell you that, the reason that they had to retire the machine was the cams on the Harvest tapes wore out and were irreplaceable. They couldn't do, and so that's why they retired it. John?
Were those decrypted messages plain text, or did that include decipherment?
I don't know. I don't know what they were examining for. But one of the things What is it done?
I don't know, with all these different offsets, it looks like they're trying to see whether, if it says dear sir, at different places.
Yeah, it could very well be looking for patterns, which was of course the primary thing that they would do. And then there's a 1980 paper which was published in the annals, IEEE Annals of History, that said that Harvard, in which Snyder from NSA was looking at the implication, the influences of the NSA work on computer technology, and these are three of the points he made as far as Harvest is concerned. Is that it was used on jobs not even conceivable on any other computer, and many technological advances impacted the future of IBM systems, and he had a list of these. It was the point of the paper, and this is one thing that was particularly intrigued me. He said, Harvest's most important effect was undoubtedly on the engineers who designed it, since the program brought out the best in all who were involved. And I think certainly what it did for me was to make me very optimistic about what one could do. I mean, even though it took us twice as long to do it when we started, or not quite twice as long, but it was the fact that we did that much in that period of time, from 1957, that was done in that period of time actually, is rather a rather amazing result, and it was done with a relative to today, small group of people. So, well, the Stretch Harvest software, which was developed pretty much by the same group, and IBM did all of the software for this, I think it got to at most about 150 people, and that was everything. Huh?
That's a fair size project.
Right. But the compiler itself is really very small.
How did the people debug their stuff? What kind of debugging tools?
Well, that's it. This pre-run was intended as a sort of debugger, but there wasn't any simulator for it. The pre-run was sort of checking on the flows through, but there wasn't any simulator for it. And I don't know how they knew when they got the right answer, or if it mattered, as long as they were close. What?
Well, I have a whole string of questions that I'm afraid I suspect you don't know the answers to.
I'm sure that's true.
There's been a steady stream of what I think is misinformation, I believe starting with an article 20 years ago in Mother Jones and repeated in Bamford's Puzzle Palace, to the effect that Harvest was used on voice recognition problems. Do you have any instinct, any knowledge?
Well, my suspicion is, sure, they picked up telephone messages. That's probably what it was. But whether it was on then, and it was just an encoding of those messages. I mean, radio messages, all of those. But I don't think that they did voice recognition. If you're referring to speech recognition.
Well, the suggestion, I think, was something that it was essentially involved with some kind of voice intercept technology,
Oh, sure.
and whether it's probably recognizing speakers as opposed to, or recognizing language or something. I don't trust the informants enough to ask any such level of detail.
I'd be amazed that if it were used for speaker recognition. It just also wasn't. Oh, yes. Yeah. Right.
My more other question is, it's some of what you showed early on looked to me awful. I wonder if you knew anything about the roots of this in the extensive NSA lore of doing things with card sorters that dates back into the 30s. Somehow I think it looks to me, those modes you listed look awfully like they were building themselves a super fast card sorter to do correlations.
Absolutely, and that's what the programming was about. In fact, they even talk about that a little bit in Snyder's paper. I think he may refer to that as what you actually down at the assembly level, not at the alpha level, but at the assembly level. It was actually you'd work with timing sheets, and you'd actually connect, you know, almost like connecting these things up, PCs up, and then stacking up the next. It was really at that level. Yes, I think that that's the case. And they were certainly had huge input. Well, in fact, I would guess the hardware was largely designed by them. I don't know that. But again, it was probably playing the same role of they're working on what they wanted very specifically, and then the IBM engineers saying what could be done. And just as the role with the alpha language, with the compilers, with the software, was they designing this, and then we would, you know, try to realize it or say it can't be done, negotiate on it in that way. Though in some of the alpha language, we certainly had some. I was very disappointed that we didn't get into some things into the alpha language that I thought would be interesting, which had to do with naming index sets associated with the data descriptors.
I have a question sort of related to WITS, by the way. The tractor tapes, I heard that they were basically multimodal. They were both binary and digital, so that they could not only take digital data but also stream. The impression was audio as well as video. They wanted to do that.
So there were bits
They
at
were
the bottom.
character. Yeah.
There
What'd you
were
say,
all
Norm?
bits at the bottom. Just like
Bits all the way down.
all bits at
Right. Question back here?
Two questions. The names Harvest, Stretch, Alpha, is there any significance to the choice of the names?
Not that I know of.
I thought that Harvest and Tractor in particular were part of a larger project, Farm Boy.
Yes,
And
Farm-
I used to
Farm-
know some
you're right,
other,
you're right.
there's
There was-
one more code word in there.
Yeah, there was Farm Boy and there was Farmer also.
Well, stretch meant they were going to stretch their goals.
Right, right. And the Stretch project, which was started 55, actually ended 55, went through various morphings as to what it would be. And Farm, now that you mention it, Farmer was a piece, was a variant of that early, as Harvest was being brought into
And
put
as
together with Stretch.
a second question, when you were enumerating